Hello, and welcome to tonight's Cosmic Journey. I'm the Drowsy Professor, and together we'll travel into the heart of ancient stars to witness the birth of every element that makes up our world and our very bodies. As you settle into this stellar story of creation written in the language of physics and time, let me know where in the world you're resting tonight and what time the stars are shining above your corner of the universe. Now, find your most comfortable position. Close your eyes and imagine drifting peacefully through the cosmos. And let's journey together into the ancient furnaces where the elements themselves were born. Deep within the heart of every star that has ever shone in the vast darkness of space burns an ancient furnace that operates with such patient precision that it transforms the very fabric of matter itself, taking the simplest element in the universe, hydrogen, and through the gentle alchemy of nuclear fusion, forging it into all the heavier elements that would eventually become planets, mountains, oceans, and the very atoms that flow through your bloodstream as you rest peacefully tonight, beneath the light of stars that are continuing this cosmic work of elemental creation. Picture yourself floating gently through the cosmos, approaching one of these stellar furnaces from the safety of vast distance, watching as its surface radiates light that began its journey in the unimaginably dense and hot core, where temperatures reach tens of millions of degrees and pressures crush matter to densities beyond anything we experience on Earth. Yet even under these extreme conditions, the process of element creation unfolds with remarkable gentleness, each fusion reaction adding just a tiny increment of mass to create heavier nuclei while releasing the energy that powers the star's brilliant glow. The story of element creation begins not with violence, but with the patient gathering of matter in the early universe, when gravity slowly pulled together vast clouds of primordial hydrogen and helium that had been created in the first few minutes after the Big Bang. These clouds, spanning light years in diameter, contracted so gradually that millions of years passed as they slowly compressed under their own gravitational attraction, warming gently as gravitational potential energy converted to heat until their centers reached the critical temperature needed to ignite nuclear fusion. As you breathe slowly and naturally in this moment, you can imagine the birth of the first stars as moments of gentle awakening rather than explosive ignition, with nuclear fusion beginning softly in stellar cores as hydrogen nuclei overcame their natural electrical repulsion and merged to form helium, releasing energy that gradually balanced the inward pull of gravity and established the stable, long-term burning that would continue for millions or billions of years. These first-generation stars were massive beyond anything we see in today's universe, containing perhaps 100 or even 200 times as much matter as our Sun, and their enormous mass created the intense gravitational pressures necessary to compress their cores to the extreme densities where heavier elements could be forged. These stellar giants burned brightly and died relatively quickly, but during their lifetimes they performed the crucial work of creating the first heavy elements that would seed the universe with the raw materials for planets and life. The nuclear furnaces within these stellar cores operate according to principles that seem almost magical in their ability to transform matter, yet they follow the precise laws of quantum mechanics and thermodynamics with perfect consistency. At the temperatures and pressures that exist in stellar cores, atomic nuclei move with such energy that they can overcome the electrical forces that normally keep them apart, allowing the strong nuclear force to bind them together into new, heavier nuclei, while releasing the binding energy that powers stellar luminosity. Picture the interior of a stellar core as a realm where matter exists in a state completely foreign to our everyday experience, with temperatures so high that atoms are completely ionized and nuclei move as bare particles through a sea of free electrons, while pressures so intense compress this nuclear soup to densities where a teaspoon of material would weigh as much as a mountain. Yet within this extreme environment, the laws of physics operate with the same precision that governs the gentle chemical reactions occurring in your body as you rest tonight. The fusion reactions that occur in stellar cores proceed through carefully orchestrated sequences of nuclear transformations, each step requiring precise conditions of temperature, pressure, and nuclear physics to proceed at rates that can sustain stellar burning for millions or billions of years. These reaction chains begin with the simplest possible fusion process, the conversion of hydrogen into helium, but eventually progress through increasingly complex sequences that build successively heavier elements until the star has forged nuclei as massive as iron and nickel. The timescales involved in stellar element creation span the vast reaches of cosmic time, with main sequence stars like our Sun steadily fusing hydrogen into helium for billions of years, while the more massive stars that create heavier elements burn through their nuclear fuel much more rapidly, but still require millions of years to progress through the successive stages of element synthesis that build carbon, oxygen, silicon, and iron in their cores. Consider how the energy that powers every star's luminosity comes from the tiny difference in mass between the reactant nuclei and the products of fusion. With Einstein's famous equation, E=mc² governing the conversion of mass into energy that provides the outward pressure needed to balance gravitational collapse, while simultaneously sending light and heat streaming into space to illuminate planets and warm the surfaces where life might eventually emerge. The stellar nucleosynthesis that creates heavy elements represents one of the universe's most patient and productive manufacturing processes, with each star serving as a cosmic factory that operates continuously for millions or billions of years, gradually converting lighter elements into heavier ones while distributing the energy released from these nuclear transformations throughout space in the form of starlight that travels across vast distances to illuminate other worlds. The first elements created in stellar cores beyond the primordial hydrogen and helium included carbon, nitrogen, and oxygen, the fundamental building blocks of organic chemistry that would eventually become essential components of life. These elements formed through nuclear fusion processes that required precise balances of temperature, pressure, and stellar mass, demonstrating how the conditions for life were gradually assembled through stellar evolution over cosmic time. Picture the moment when carbon first formed in the core of an ancient star through the triple alpha process, where 3 helium nuclei combined in a remarkable sequence of nuclear reactions that required temperatures exceeding 100 million degrees and occurred through quantum mechanical tunneling effects that allowed nuclear fusion to proceed despite seemingly insurmountable energy barriers. The stellar cores where element creation occurs represent some of the most extreme environments in the universe. Yet they also demonstrate the remarkable stability and precision of natural processes operating over vast time scales. These nuclear furnaces burn steadily for millions or billions of years, maintaining the precise balance between gravitational compression and radiation pressure that allows controlled nuclear fusion to proceed at rates that can sustain stellar luminosity while gradually building heavier elements. The convection processes that operate within stellar cores help mix newly created elements throughout the stellar interior, while bringing fresh nuclear fuel into the fusion zones where element creation occurs. These convective motions operate like vast, slow circulation systems that ensure efficient mixing of stellar material, while maintaining the temperature and pressure gradients necessary for continued nuclear burning. As you settle deeper into rest tonight, you can appreciate how the stars visible in the night sky represent active sites of ongoing element creation, with nuclear fusion continuing to forge new atoms of carbon, oxygen, and other heavy elements in stellar cores throughout the galaxy. The starlight that reaches Earth carries energy that was released during these nuclear transformations, connecting us directly to the elemental creation processes occurring in stellar furnaces across the cosmos. The chemical evolution of the universe proceeds through stellar nucleosynthesis as successive generations of stars create heavy elements and distribute them through space when their lives end, gradually enriching the interstellar medium with the raw materials needed to form planets and eventually support the complex chemistry that makes life possible. The mass-energy relationship that governs nuclear fusion ensures that stellar nucleosynthesis can continue only as long as fusion reactions release energy, by combining lighter nuclei into heavier ones. This fundamental physical principle means that stellar cores can build elements only up to iron and nickel, beyond which fusion reactions would require energy input rather than releasing energy, setting the stage for the dramatic events that occur when massive stars exhaust their nuclear fuel. In the luminous heart of every star, hydrogen nuclei engage in an elegant molecular dance that has been choreographed by the fundamental forces of physics, a dance so gentle and precise that 4 hydrogen nuclei can overcome their natural repulsion and merge together to create a single helium nucleus, while releasing exactly the right amount of energy to power stellar luminosity for billions of years. This is the proton-proton chain reaction, the most fundamental and important nuclear process in the universe, responsible for powering the vast majority of stars and creating the first step in the cosmic ladder of element synthesis. Picture this stellar dance beginning with the simplest possible interaction between 2 hydrogen nuclei, 2 single protons, as they approach each other in the dense, hot plasma of a stellar core. At the enormous temperatures that exist in stellar interiors, these protons move with such kinetic energy that they can overcome the electrical repulsion that normally keeps positively charged particles apart, allowing them to come close enough for the strong nuclear force to bind them together in a process that seems almost miraculous in its delicate precision. The first step in hydrogen fusion requires one of the 2 protons to undergo a remarkable transformation, converting spontaneously into a neutron through the weak nuclear force, while simultaneously emitting a positron and a neutrino. This transformation creates a deuterium nucleus, heavy hydrogen, that contains 1 proton and 1 neutron bound together by the strong nuclear force. The probability of this conversion occurring during any single proton-proton collision is extraordinarily small, which explains why stellar hydrogen burning proceeds at such a gentle, sustainable rate that can continue for billions of years. As you breathe slowly and peacefully, you can imagine the vast number of these proton-proton interactions occurring every second in a stellar core, with countless hydrogen nuclei colliding and bouncing apart. But occasionally, through the quantum mechanical probability that governs weak nuclear interactions, 1 collision results in the formation of deuterium and takes the first step toward building helium from hydrogen while releasing the energy that will eventually reach us as starlight. The deuterium nucleus created in this first fusion step quickly encounters another hydrogen nucleus in the dense stellar plasma. And because deuterium has both a proton and a neutron, this second collision can proceed much more readily than the original proton-proton interaction. The deuterium and hydrogen merge to form helium-3, a light isotope of helium containing 2 protons and 1 neutron, while releasing additional energy and demonstrating how each step in the fusion chain becomes progressively easier once the initial barrier of proton-proton conversion has been overcome. Picture the helium-3 nucleus as it moves through the stellar plasma, eventually encountering another helium-3 nucleus that was created through the same sequence of reactions. When 2 helium-3 nuclei collide with sufficient energy, they merge together and then immediately split apart in a different configuration, ejecting 2 protons while leaving behind a stable helium-4 nucleus containing 2 protons and 2 neutrons, the final product of hydrogen fusion and the second most abundant element in the universe. The elegance of this proton-proton chain lies in its perfect balance of nuclear physics and stellar conditions, with each reaction step proceeding at precisely the rate needed to maintain stellar stability while gradually converting hydrogen into helium over the vast timescales of stellar evolution. The energy released during each complete sequence provides exactly the radiation pressure needed to balance gravitational collapse, creating the hydrostatic equilibrium that allows stars to shine steadily for billions of years. The neutrinos produced during the first step of hydrogen fusion provide a remarkable window into stellar interiors, as these nearly massless particles interact so weakly with matter that they can escape directly from stellar cores and travel across space at nearly the speed of light. The neutrinos reaching Earth from the Sun carry direct information about nuclear reactions occurring in the solar core at this very moment, providing real-time evidence of hydrogen fusion happening 93 million miles away. Imagine these solar neutrinos passing through your body right now as you rest peacefully, billions of them streaming through every square centimeter of Earth's surface every second, carrying with them the signature of nuclear transformations that began in the Sun's core and will continue for several billion more years. These neutrinos connect us directly to stellar nucleosynthesis, allowing us to observe the nuclear alchemy that powers our star and provides the energy that makes life on Earth possible. The temperature dependence of hydrogen fusion creates a natural thermostat that regulates stellar energy production with remarkable precision. If a star's core becomes too hot, fusion reactions proceed more rapidly, releasing more energy and creating radiation pressure that causes the core to expand and cool. If the core becomes too cool, fusion rates decrease, reducing radiation pressure and allowing gravitational compression to heat the core back to optimal fusion temperatures. This self-regulating mechanism ensures that hydrogen-burning stars maintain stable luminosity over vast periods of time, providing the steady energy output that allows planetary systems to develop stable climates suitable for the evolution of complex chemistry and eventually life. The Sun has maintained this stable hydrogen burning for approximately 4.5 billion years and will continue doing so for several billion more years. The quantum mechanical tunneling that enables hydrogen fusion represents one of the most remarkable phenomena in stellar physics, allowing nuclear reactions to occur even when protons lack the classical energy needed to overcome electrical repulsion. According to quantum mechanics, particles can tunnel through energy barriers that would be insurmountable according to classical physics. And this quantum effect makes stellar hydrogen burning possible at the relatively low temperatures found in stellar cores. Picture this quantum tunneling as protons approaching the energy barrier created by electrical repulsion, then mysteriously appearing on the other side of the barrier where the strong nuclear force can bind them together, even though they lack the energy to climb over the barrier through classical means. This quantum mechanical phenomenon operates according to probability distributions that ensure fusion occurs at precisely the rates needed to sustain stellar burning over cosmic timescales. The hydrogen fusion occurring in stellar cores converts approximately 0.7% of the rest mass of hydrogen nuclei into energy according to Einstein's mass-energy equivalence, providing the enormous energy output that powers stellar luminosity while gradually reducing the total mass of the star through the conversion of matter into radiation. This mass-energy conversion represents one of the most efficient energy production mechanisms known in nature. The convection zones that develop in many stellar interiors help transport the energy released by hydrogen fusion from the core toward the stellar surface, while mixing hydrogen fuel into the fusion zones and distributing the helium products of fusion throughout the stellar interior. These convective flows operate like vast circulation systems that ensure efficient energy transport while maintaining the nuclear fuel supply needed for continued hydrogen burning. Consider how the helium produced by hydrogen fusion gradually accumulates in stellar cores, slowly changing the chemical composition of stars and affecting their internal structure and evolution. As helium builds up in stellar cores, it increases the mean molecular weight of the stellar material and affects the pressure and temperature distributions that control stellar structure, eventually leading to changes in stellar luminosity and size as stars age. The isotopic products of stellar hydrogen fusion include not only helium-4, but also trace amounts of deuterium, helium-3, and other light nuclei that provide detailed signatures of nuclear processes operating in stellar cores. The precise ratios of these isotopes depend on stellar mass, temperature, and evolutionary stage, allowing astronomers to use spectroscopic observations of stellar atmospheres to infer conditions in stellar interiors. The energy transport from stellar cores to stellar surfaces occurs through radiative diffusion in most stars. with photons created by nuclear fusion undergoing countless absorption and re-emission events as they slowly work their way outward through stellar interiors over periods of thousands or millions of years. The photons that reach Earth as sunlight began their journey in the solar core long before human civilization existed. Picture individual photons created by hydrogen fusion in the sun's core beginning a random walk journey through the solar interior, being absorbed and re-emitted countless times by atoms in the stellar plasma, gradually working their way outward through the radiative zone over periods of approximately 100,000 years before finally reaching the solar surface and streaming across space to illuminate Earth. The stellar lifetime determined by hydrogen fusion depends critically on stellar mass, with more massive stars burning their hydrogen fuel much more rapidly than less massive stars despite having larger initial fuel supplies. This relationship between stellar mass and lifetime ensures that the smallest hydrogen-burning stars can continue fusing hydrogen for trillions of years, far longer than the current age of the universe. The brown dwarf objects that lack sufficient mass to sustain hydrogen fusion represent failed stars that never achieve the core temperatures and pressures needed to ignite nuclear burning, instead slowly cooling over cosmic time while gradually contracting under their own gravity. These objects demonstrate the precise mass threshold required for hydrogen fusion and stellar ignition. The white dwarf stars that represent the endpoints of low-mass stellar evolution consist primarily of carbon and oxygen produced by helium fusion during earlier phases of stellar evolution, with hydrogen fusion having ceased when the stellar envelope was expelled to form planetary nebulae. These stellar remnants provide insights into stellar nucleosynthesis processes and the ultimate fate of hydrogen-burning stars. The hydrogen burning that occurs in stellar cores represents just the first step in stellar nucleosynthesis, providing the foundation for more complex nuclear processes that create heavier elements in massive stars. As stellar cores exhaust their hydrogen fuel, the stage becomes set for helium fusion and the creation of carbon, oxygen, and other heavy elements that are essential components of planets and life. Tonight, as you drift toward deeper rest, you can appreciate how the hydrogen fusion occurring in stellar cores throughout the galaxy continues the ancient dance that began with the first stars, steadily converting the most abundant element in the universe into helium, while releasing the energy that powers stellar luminosity and creates the conditions necessary for planets, chemistry, and life. This gentle nuclear alchemy connects us to the fundamental processes that govern cosmic evolution and demonstrates the remarkable precision with which natural laws operate to create the universe we observe today. As stars age and steadily consume the hydrogen fuel in their cores, they gradually approach a pivotal moment in their evolution when the familiar dance of proton-proton fusion begins to slow, and stellar cores must find new sources of nuclear energy to maintain the delicate balance between gravitational collapse and radiation pressure. This transition marks the beginning of helium fusion, a more complex but equally elegant process that creates carbon, nitrogen, and oxygen, the fundamental elements of organic chemistry that would eventually become the building blocks of planets, atmospheres, oceans, and all living things. Picture a star that has spent hundreds of millions or billions of years steadily converting hydrogen into helium in its core, gradually accumulating a dense reservoir of helium nuclei that cannot fuse under the relatively moderate conditions that sustain hydrogen burning. As hydrogen becomes depleted in the stellar core, the nuclear fires that have maintained stellar stability begin to dim, and gravitational compression slowly gains the upper hand, gently squeezing the stellar core to higher densities and temperatures until the helium nuclei finally possess enough energy to overcome their mutual electrical repulsion. The ignition of helium fusion requires temperatures exceeding 100 million degrees, nearly 10 times hotter than the conditions needed for hydrogen burning, demonstrating the progressively more extreme conditions required to fuse heavier nuclei as stellar evolution proceeds. Yet when helium fusion finally begins, it does so with the same gentle precision that characterizes all stellar nuclear processes, following quantum mechanical rules that ensure sustainable burning over millions of years. As you breathe slowly and peacefully tonight, you can imagine the moment when helium fusion ignites in an aging stellar core, not as a violent explosion, but as a gradual warming that spreads through the helium-rich interior as nuclear reactions find new pathways for converting matter into energy. This helium-burning phase represents a remarkable renaissance in stellar evolution, allowing stars to continue shining while beginning the crucial work of building the heavier elements that make complex chemistry possible. The primary helium fusion process, known as the triple alpha reaction, represents one of the most remarkable and improbable nuclear sequences in stellar physics, requiring 3 helium nuclei, alpha particles, to combine almost simultaneously to create a carbon nucleus. This reaction proceeds through an extraordinarily delicate quantum mechanical dance that depends on a precise resonance discovered by astronomer Fred Hoyle, who realized that carbon production in stellar cores requires nuclear energy levels to be tuned to within a fraction of a percent of their observed values. Picture this triple alpha process unfolding in the hot, dense plasma of a helium-burning stellar core, where helium nuclei move with enormous kinetic energy, but must overcome the increasingly strong electrical repulsion that affects all nuclear fusion as nuclei become more highly charged. The first step involves 2 helium nuclei combining to form the unstable nucleus beryllium-8, which normally decays in a tiny fraction of a second, but occasionally encounters a 3rd helium nucleus before it can disintegrate. The formation of carbon through helium fusion represents a crucial threshold in cosmic chemical evolution, as carbon nuclei provide the foundation for all subsequent heavy element synthesis in stellar cores. Once carbon begins accumulating in stellar interiors, it opens pathways for creating nitrogen and oxygen through additional nuclear reactions that gradually build the periodic table of elements 1 nucleus at a time. The carbon nuclei created by helium fusion can capture additional helium nuclei to form oxygen through a process that occurs readily under helium-burning conditions, demonstrating how stellar nucleosynthesis proceeds through step-by-step nuclear additions that build progressively heavier elements. This carbon plus helium reaction creates oxygen-16, the most abundant isotope of oxygen and a crucial component of water, rocky planets, and biological molecules. Imagine oxygen nuclei forming in stellar cores through this patient process of nuclear construction, each oxygen atom representing the combination of a carbon nucleus with a helium nucleus under conditions of extreme temperature and pressure that exist nowhere else in the universe except in stellar interiors and the aftermath of stellar explosions. The oxygen you breathe tonight was forged in stellar cores that underwent helium burning millions or billions of years ago. The neon and magnesium that form through continued helium capture by carbon and oxygen nuclei represent additional steps in the stellar assembly line that builds light elements, with each nuclear addition requiring slightly different conditions of temperature, pressure, and reaction probability. These elements form in smaller quantities than carbon and oxygen, but play important roles in planetary geology and biological chemistry. The convective mixing that occurs during helium burning helps distribute newly created carbon and oxygen throughout stellar cores, while bringing fresh helium fuel into the fusion zones where nuclear reactions proceed most rapidly. These convective motions operate on timescales of hundreds or thousands of years, gradually stirring stellar interiors to ensure efficient fuel utilization and uniform composition throughout the helium-burning region. Picture vast convective currents moving through the interior of a helium-burning star, carrying carbon and oxygen nuclei from the nuclear furnace at the stellar center toward outer regions, while transporting helium fuel inward to sustain continued fusion reactions. These circulation patterns help maintain the temperature and composition gradients needed for stable helium burning, while preventing the accumulation of nuclear reaction products that might inhibit continued fusion. The energy released by helium fusion provides approximately 10% as much energy per unit mass as hydrogen fusion, requiring helium-burning stars to consume their nuclear fuel more rapidly to maintain the same luminosity they achieve during hydrogen burning. This reduced energy yield means that helium-burning phases last much shorter periods than hydrogen-burning phases, typically millions rather than billions of years for stars similar to the Sun. The stellar structure changes that accompany helium burning often cause stars to expand significantly and cool their surface temperatures, creating the red giant and supergiant phases that characterize evolved stellar evolution. During these phases, stars may expand to hundreds of times their original size, while maintaining approximately the same total energy output, demonstrating how stellar nucleosynthesis affects not only chemical composition, but also physical structure and appearance. Consider how red giant stars represent active sites of carbon and oxygen production, with helium fusion creating these essential heavy elements in stellar cores, while the expanded stellar atmospheres begin the process of mass loss that will eventually return processed stellar material to the interstellar medium. These evolved stars serve as crucial intermediaries in cosmic chemical evolution, creating heavy elements and beginning their distribution throughout space. The asymptotic giant branch phase that many stars experience during their later evolution involves alternating periods of helium and hydrogen burning in shells surrounding an inert carbon-oxygen core, creating thermal pulses that periodically dredge up freshly synthesized carbon and oxygen to stellar surfaces, where they can be incorporated into stellar winds and eventually dispersed into space. Picture these thermal pulses as gentle, periodic hiccups in stellar evolution that bring carbon and oxygen created in stellar interiors to stellar surfaces, where they become available for mass loss processes. These pulses operate on timescales of thousands to hundreds of thousands of years, gradually enriching stellar atmospheres with heavy elements while preparing for the eventual ejection of processed stellar material through stellar winds and planetary nebula formation. The nitrogen production that occurs during helium burning involves more complex nuclear reaction networks that convert carbon and oxygen nuclei into nitrogen through processes that depend on the specific temperature and density conditions in stellar cores. This nitrogen synthesis demonstrates how stellar nucleosynthesis creates not just individual elements, but entire suites of chemically related elements that become available for incorporation into planets and biological systems. The isotopic variations produced by stellar helium burning create distinctive signatures that allow astronomers to identify carbon and oxygen that originated in stellar cores versus other nucleosynthetic processes. These isotopic fingerprints provide crucial evidence for understanding stellar evolution and the sources of heavy elements in the galaxy. The stellar winds that begin during helium burning phases represent the first significant mechanism for returning processed stellar material to the interstellar medium, enriching the galactic chemical inventory with carbon, oxygen, and other products of stellar nucleosynthesis. These winds blow gently but persistently, carrying away stellar atmosphere at rates that gradually expose the nuclear processing regions of stellar interiors. Imagine stellar winds as gentle but persistent breezes that carry carbon and oxygen nuclei away from aging stars and into the spaces between stars, where they will eventually become incorporated into new generations of star formation and planet building. These winds operate continuously over millions of years, gradually dispersing the products of stellar nucleosynthesis throughout the galaxy. The planetary nebulae that form when low-mass stars shed their outer atmospheres create some of the most beautiful displays in astronomy, while performing the crucial function of distributing carbon and oxygen produced by helium burning throughout the interstellar medium. These glowing shells of ionized gas represent the final gifts of aging stars to the cosmic chemical inventory. Picture planetary nebulae as cosmic flowers blooming in space, with intricate patterns of glowing gas illuminated by the hot white dwarf stars at their centers, each nebula representing the life's work of stellar nucleosynthesis being gently released into space, where we'll seed future generations of stars and planets with the heavy elements essential for rocky planet formation and organic chemistry. The white dwarf stars that remain after planetary nebula ejection consist primarily of carbon and oxygen created during helium burning, representing stellar cores that have exhausted their nuclear fuel and settled into a final state of gravitational equilibrium. These stellar remnants provide long-term repositories for carbon and oxygen, while serving as cosmic laboratories for studying the products of stellar nucleosynthesis. The carbon stars that develop during certain phases of stellar evolution display spectroscopic evidence of carbon production in their atmospheres, with carbon absorption lines indicating surface abundances of carbon that exceed oxygen abundances. These stars provide direct observational evidence of carbon synthesis in stellar interiors and its transport to stellar surfaces through convective dredge-up processes. The stellar mass dependence of helium burning determines which stars can produce significant quantities of carbon and oxygen through this process, with stars less massive than about 8 solar masses experiencing helium burning in their cores, while more massive stars undergo helium burning as a brief phase in their progression toward even more exotic nuclear burning stages that create elements heavier than oxygen. The chemical evolution of galaxies proceeds through the contributions of countless stars that undergo helium burning and distribute carbon and oxygen into the interstellar medium, gradually increasing the heavy element content of galactic gas reservoirs and enabling the formation of rocky planets and the development of carbon-based chemistry that makes life possible. Tonight, as you settle deeper into peaceful rest, you can appreciate how the carbon in your body and the oxygen you breathe represent gifts from ancient stars that underwent helium burning millions or billions of years ago, creating these essential elements through nuclear alchemy and distributing them through space, where they eventually became incorporated into the solar system and Earth. The stellar forges that created these life-enabling elements continue their work throughout the galaxy, ensuring that the universe becomes progressively richer in the heavy elements needed for planets, chemistry, and life as cosmic evolution proceeds through stellar nucleosynthesis. In the massive stars that dwarf our Sun by factors of 10, 20, or even 50 times, the story of element creation continues far beyond the carbon and oxygen production that marks the endpoint of nucleosynthesis in smaller stars. Progressing through increasingly exotic nuclear burning stages that forge successively heavier elements in stellar cores that reach temperatures and densities almost beyond imagination. These stellar giants, destined for dramatic endings as supernovae, spend their final millions of years engaged in rapid-fire nuclear synthesis that creates silicon, sulfur, argon, calcium, titanium, chromium, manganese, iron, and nickel, building the periodic table all the way up to the most stable nuclear configurations in nature. Picture one of these massive stars in its final evolutionary phases, having already exhausted hydrogen and helium in its core and now burning carbon and oxygen in a sequence of increasingly brief nuclear burning stages. The stellar core has become a complex onion-like structure with different nuclear processes occurring in concentric shells. Hydrogen burning in the outermost regions, helium burning in intermediate zones, and carbon burning near the center, while the core temperature and density continue climbing toward the extreme conditions needed for silicon burning. The carbon burning phase that precedes silicon burning creates neon, sodium, and magnesium through nuclear reactions that occur at temperatures exceeding 600 million degrees, approximately 60 times hotter than the solar core. At these extreme temperatures, carbon nuclei possess enough kinetic energy to overcome their mutual electrical repulsion and merge together, creating reactions that proceed much more rapidly than the helium burning that created the carbon fuel in the first place. As you breathe slowly and naturally tonight, you can imagine the interior of one of these massive stars as a nuclear furnace operating at temperatures that would instantly vaporize any known material, yet following the same physical laws that govern gentler nuclear processes, only accelerated and intensified by the extreme gravitational compression that massive stars create in their cores. The nuclear reactions proceed with remarkable efficiency, converting carbon into heavier elements over timescales measured in thousands rather than millions of years. The neon burning that follows carbon burning represents another step in the nuclear ladder that builds progressively heavier elements, with neon nuclei breaking apart under intense bombardment by high-energy photons, then recombining with helium nuclei to create magnesium and silicon. This process demonstrates how stellar nucleosynthesis becomes increasingly complex as temperatures rise, involving not just nuclear fusion, but also photodisintegration reactions that break apart previously synthesized nuclei to provide raw materials for building even heavier elements. Picture the stellar core during neon burning as a realm where matter exists in such extreme conditions that nuclei spontaneously break apart due to the intense radiation field, then immediately recombine in different configurations to create heavier elements. The balance between nuclear destruction and reconstruction creates a dynamic equilibrium that allows steady element synthesis while maintaining the energy production needed to support the massive stellar structure. The oxygen burning phase that follows creates silicon, sulfur, phosphorus, and other intermediate mass elements through a complex network of nuclear reactions that occur at temperatures exceeding 1.5 billion degrees. At these temperatures, oxygen nuclei can fuse directly with each other while also capturing alpha particles to build a diverse suite of elements that includes many of the components essential for rocky planet formation and biological chemistry. The stellar timescales during these advanced burning phases become progressively shorter as nuclear fuel becomes depleted more rapidly and gravitational compression accelerates stellar evolution. While hydrogen burning can sustain a massive star for millions of years and helium burning for hundreds of thousands of years, carbon burning lasts only centuries, neon burning only years, and oxygen burning mere months, demonstrating how stellar evolution accelerates dramatically as stars approach their final fate. Consider how the energy released per unit mass decreases with each successive nuclear burning stage, requiring massive stars to consume nuclear fuel at ever-increasing rates to maintain the radiation pressure needed to balance gravitational collapse. This fundamental limitation in nuclear energy production sets the stage for the dramatic events that occur when stars finally exhaust their ability to generate energy through nuclear fusion. The silicon burning that represents the final stage of stellar nucleosynthesis occurs at temperatures exceeding 3 billion degrees, creating conditions so extreme that nuclear physics operates in ways completely foreign to terrestrial experience. Under these conditions, silicon nuclei and other intermediate mass elements undergo rapid sequences of alpha particle capture and photodisintegration that gradually build nuclei with masses approaching iron and nickel. Picture silicon burning as a rapid-fire nuclear process where alpha particles, helium nuclei, are added to silicon and other intermediate nuclei at rates that can build iron peak elements in a matter of days or weeks. The nuclear reactions proceed so rapidly that stellar cores can convert significant fractions of their silicon fuel into iron and nickel almost instantaneously on astronomical timescales, creating dense concentrations of the most stable nuclei in nature. The alpha process that dominates silicon burning involves the successive addition of helium nuclei to intermediate mass elements, creating a nuclear assembly line that builds elements through the periodic table. Silicon plus alpha equals sulfur. Sulfur plus alpha equals argon. Argon plus alpha equals calcium, and so forth. With each alpha capture creating progressively heavier nuclei, while releasing energy that helps maintain stellar structure during these final burning phases. The nuclear statistical equilibrium that develops during silicon burning creates conditions where nuclear reaction rates become so rapid that the abundances of different nuclei reach equilibrium values determined by nuclear binding energies and reaction cross-sections rather than by the detailed reaction pathways that determine nucleosynthesis at lower temperatures. This equilibrium favors the production of iron and nickel, which have the highest binding energies per nucleon of all atomic nuclei. Imagine the stellar core during silicon burning as a nuclear laboratory where the fundamental properties of atomic nuclei determine which elements can exist in significant abundances, with iron and nickel emerging as the dominant products because they represent the most stable possible nuclear configurations. The physics of nuclear binding energy ensures that silicon burning naturally converges on iron peak element production regardless of the specific reaction pathways involved. The convective mixing that occurs during silicon burning helps homogenize the composition of stellar cores while distributing the heat generated by nuclear reactions throughout the burning region. These convective motions operate on timescales of hours to days, creating rapid circulation that maintains relatively uniform temperature and composition profiles despite the extremely rapid nuclear processing that characterizes silicon burning. The electron degeneracy that begins to develop in stellar cores during silicon burning creates additional pressure support that helps maintain stellar structure, even as nuclear energy production begins to decrease. This quantum mechanical pressure effect becomes increasingly important as stellar cores approach the densities where electron motion becomes relativistic, and electron pressure can contribute significantly to hydrostatic equilibrium. Picture the stellar core during silicon burning as a realm where quantum mechanics and relativity begin to influence stellar structure significantly, with electrons compressed to densities where their wave functions overlap and create degeneracy pressure that operates independently of temperature, providing a new source of structural support as nuclear energy generation approaches its fundamental limits. The isotopic composition of elements created during silicon burning reflects the specific nuclear reaction networks and equilibrium conditions that characterize these extreme stellar environments, creating distinctive signatures that allow astronomers to identify silicon burning products in meteorites and stellar spectra. These isotopic fingerprints provide crucial evidence for understanding silicon burning processes and their role in cosmic nucleosynthesis. The neutron flux that develops during silicon burning creates conditions where neutron capture reactions can begin to contribute to element synthesis, supplementing the alpha process with S-process neutron capture that creates some isotopes that cannot be produced through alpha particle addition alone. This neutron capture represents a preview of the more extensive neutron capture processes that occur during supernova explosions. The stellar wind mass loss that accelerates during the final evolutionary phases of massive stars begins to expose the nuclear processing regions created by successive burning stages, potentially allowing direct observation of silicon burning products in stellar atmospheres. These mass loss processes help distribute freshly synthesized elements into the interstellar medium even before the star undergoes its final supernova explosion. Consider how the silicon burning occurring in massive stellar cores throughout the galaxy continues the cosmic assembly line that builds the periodic table, creating the iron peak elements that form essential components of rocky planets, biological systems, and technological materials. The iron in your blood and the calcium in your bones were forged during silicon burning in massive stars that lived and died billions of years ago. The nuclear energy crisis that develops as silicon burning produces iron and nickel marks a fundamental turning point in stellar evolution, as further nuclear fusion beyond iron requires energy input rather than releasing energy. This limitation creates an insurmountable problem for stellar energy generation that sets the stage for core collapse and the dramatic events that mark the end of massive stellar evolution. The approach toward the Chandrasekhar limit during silicon burning indicates that stellar cores are approaching the maximum mass that can be supported by electron degeneracy pressure, creating instabilities that will ultimately lead to core collapse when nuclear fuel is exhausted and gravitational compression can no longer be balanced by radiation pressure or degeneracy pressure. Picture the stellar core as silicon burning nears completion, having built up a substantial reservoir of iron and nickel while approaching both the nuclear energy limit and the mass limit for stable stellar structure. The stage is now set for the dramatic transformation that will convert the massive star from a nuclear furnace into a neutron star or black hole, while explosively distributing its accumulated nucleosynthetic products throughout space. The pre-supernova structure that develops during silicon burning creates a complex stellar interior with multiple burning shells surrounding an iron core, all supported by the delicate balance between nuclear energy generation and gravitational compression that will soon be disrupted when the iron core reaches critical mass and can no longer maintain structural stability. The final moments of silicon burning represent the calm before the storm of stellar collapse, with nuclear reactions proceeding at maximum efficiency to build iron peak elements, while gravitational forces gather strength for the dramatic transformation that will mark the violent end of stellar nucleosynthesis and the beginning of explosive element distribution that enriches the galaxy with heavy elements. Tonight, as you drift toward deeper rest, you can appreciate how the silicon burning occurring in massive stellar cores represents the final chapter in peaceful stellar nucleosynthesis, creating iron and nickel through nuclear processes that follow the same physical laws governing all stellar burning stages, yet operating under such extreme conditions that they approach the fundamental limits of nuclear energy generation and stellar stability. The iron peak elements created during silicon burning provide essential building blocks for rocky planets and technological civilization, demonstrating how the most extreme stellar environments contribute to cosmic chemical evolution and the eventual emergence of complexity in the universe. In the quiet depths of space, a massive star that has burned steadily for millions of years approaches a moment of profound transformation that will convert it from a nuclear furnace into something entirely new while creating, in a span of mere seconds, more heavy elements than it produced during its entire previous lifetime. This moment marks the transition from the gentle, sustained nuclear burning that has characterized stellar evolution to the explosive nucleosynthesis that occurs during core collapse and supernova explosion, a process so energetic and creative that it forges elements that cannot be made any other way in the universe. Picture this massive star in its final moments of stable existence, having built up an iron core roughly the mass of our Sun, but compressed to a sphere only about 12 miles in diameter, with density so extreme that a teaspoon of this stellar material would weigh as much as Mount Everest. Around this iron core, concentric shells continue their nuclear burning, silicon burning just outside the core, oxygen burning further out, carbon and helium burning in outer regions, creating a complex stellar structure that has taken millions of years to develop, but will be transformed in less time than it takes to blink an eye. The iron core represents a nuclear dead end, composed of the most stable nuclei in nature, which cannot be fused to release energy without violating the fundamental principles of nuclear physics. As silicon burning adds more iron and nickel to this core, its mass gradually approaches the Chandrasekhar limit, approximately 1.4 solar masses, beyond which electron degeneracy pressure cannot provide sufficient support to balance gravitational compression. The approach to this critical mass creates subtle instabilities that build slowly and invisibly toward the moment of catastrophic collapse. As you breathe slowly and peacefully tonight, you can imagine this stellar core balanced on the edge of gravitational collapse, with quantum mechanical forces providing just enough pressure to maintain stability, while nuclear reactions in surrounding shells continue adding mass that brings the core ever closer to its stability limit. The star appears outwardly normal, continuing to shine steadily while its interior approaches one of the most dramatic transformation events possible in nature. The moment of core collapse begins when the iron core exceeds the Chandrasekhar limit and electron degeneracy pressure can no longer balance gravitational compression. In a fraction of a second, the core contracts from a diameter of 12 miles to barely 6 miles, crushing atomic nuclei together with such force that protons and electrons merge to form neutrons, while neutrinos stream away, carrying enormous amounts of energy. This collapse releases gravitational potential energy equivalent to the total energy output of our Sun over its entire 10 billion year lifetime. Picture this core collapse as a moment of profound transformation rather than violent destruction, with matter transitioning from one state to another according to the fundamental laws of physics, operating under conditions that push the boundaries of what matter can become. The collapse proceeds with remarkable precision, converting stellar material into neutron matter while creating conditions of temperature and density that enable nuclear processes impossible under any other circumstances. The neutron star that forms during core collapse represents one of the most exotic forms of matter in the universe, with density so extreme that atomic nuclei dissolve into a fluid of neutrons, protons, and electrons governed by quantum mechanics and general relativity. This newly formed neutron star, barely 10 miles in diameter but containing more mass than our Sun, creates gravitational fields so intense that space and time become noticeably curved in its vicinity. The supernova shock wave that forms when core collapse suddenly halts and rebounds creates a blast wave that propagates outward through the stellar interior at speeds of 30,000 miles per second, heating stellar material to temperatures exceeding 100 billion degrees and creating conditions where explosive nucleosynthesis can forge elements that peaceful stellar burning cannot produce. This shock wave represents the delivery mechanism that will distribute the star's accumulated nucleosynthetic products throughout space. Imagine this shock wave as it sweeps through the layered stellar interior, encountering and processing the products of millions of years of nuclear burning while simultaneously creating new elements through processes that occur nowhere else in the universe. The shock heating creates temperatures so extreme that nuclear physics operates in regimes completely different from those governing peaceful stellar fusion, enabling rapid neutron capture and other exotic nuclear processes. The process, nucleosynthesis, that occurs during supernova explosions creates approximately half of all elements heavier than iron. Through rapid neutron capture, occurring faster than radioactive decay, can eliminate unstable nuclei. This process builds atomic nuclei far from the valley of beta stability, creating neutron-rich isotopes that subsequently decay to produce stable heavy elements including gold, platinum, uranium, and countless others that cannot be synthesized through any other known mechanism. Picture neutrons flooding through stellar material during supernova explosion at densities so extreme that atomic nuclei capture neutron after neutron in rapid succession, building up heavy neutron-rich isotopes that would normally be impossible to create because they decay too quickly under normal conditions. The process operates like a cosmic assembly line running at maximum speed, building the heaviest elements in nature during the brief moments when extreme neutron fluxes exist. The alpha-rich freeze-out that occurs in certain regions of supernova ejecta creates additional heavy elements through rapid alpha particle capture at high temperatures, supplementing our process nucleosynthesis with alternative pathways for heavy element synthesis. These processes demonstrate the remarkable creativity of explosive nucleosynthesis, which can forge elements through multiple parallel mechanisms operating simultaneously during supernova explosions. The neutrino flux generated during core collapse carries away approximately 99% of the energy released during supernova explosion, with these weakly interacting particles streaming directly from the neutron star formation region at nearly the speed of light. The detection of neutrinos from supernova explosions provides direct observational evidence of core collapse and neutron star formation occurring in real time across cosmic distances. Consider how supernova neutrinos provide a unique window into the most extreme nuclear physics processes in the universe, carrying information about matter under conditions of temperature, density, and neutron excess that cannot be reproduced in terrestrial laboratories. These neutrinos connect us directly to stellar collapse events occurring throughout the galaxy and beyond, allowing observation of nuclear transformation processes that operate only during these dramatic stellar endpoints. The explosive burning that occurs as the supernova shock wave propagates through stellar shells creates additional elements through conventional nuclear fusion operating under the extreme conditions generated by shock heating. Silicon burning, oxygen burning, and other fusion processes occur explosively rather than gradually, creating distinctive isotopic signatures that can be identified in supernova remnants and meteoritic inclusions. The nucleosynthetic yield from a single supernova explosion includes elements from across the periodic table, with different stellar mass ranges and explosion mechanisms producing characteristic abundance patterns that contribute to galactic chemical evolution. A typical supernova can produce several solar masses of oxygen, approximately one solar mass of silicon and iron, and smaller but significant quantities of all elements from carbon through uranium. Picture the incredible productivity of supernova and nucleosynthesis, with a single stellar explosion creating more heavy elements than our Sun will produce through peaceful nuclear fusion, during its entire 10 billion year lifetime. The efficiency of explosive element synthesis demonstrates the importance of stellar death in cosmic chemical evolution, with supernova explosions serving as the primary source of elements essential for rocky planet formation and biological chemistry. The supernova light curve that characterizes stellar explosions results from the radioactive decay of unstable isotopes created during explosive nucleosynthesis, particularly nickel 56, which decays through cobalt 56 to stable iron 56, while powering supernova luminosity for months or years after the initial explosion. This radioactive heating creates the extended energy source that makes supernovae visible across cosmic distances and provides observational signatures of nuclear processes occurring during explosion. The element mixing that occurs during supernova explosion helps homogenize the composition of stellar ejecta, while creating the chemical diversity observed in supernova remnants and the interstellar medium. Rayleigh-Taylor instabilities and other hydrodynamic processes mix materials from different stellar burning shells, creating complex abundance patterns that reflect both the layered structure of pre-supernova stars and the chaotic dynamics of explosive mass ejection. Imagine the complex fluid dynamics operating during supernova explosion as shock waves, instabilities, and turbulent mixing create intricate patterns of element distribution throughout the expanding stellar debris. These mixing processes help ensure that heavy elements synthesized in stellar cores become available for incorporation into future generations of star formation rather than remaining locked in compact stellar remnants. The supernova remnant expansion that follows stellar explosion creates expanding shells of hot, chemically enriched gas that interact with the surrounding interstellar medium for thousands of years, gradually mixing stellar, nucleosynthetic products throughout galactic environments. These remnants serve as cosmic laboratories for studying explosive nucleosynthesis while providing the mechanism for distributing heavy elements on galactic scales. The chemical signatures preserved in meteorites and stellar atmospheres provide detailed records of supernova nucleosynthesis, with isotopic anomalies and abundance patterns serving as forensic evidence for the nuclear processes operating during stellar explosions. These observations allow astronomers to reconstruct the history of galactic chemical evolution and understand the contributions of different stellar populations to cosmic element synthesis. The stellar mass dependence of supernova nucleosynthesis determines which stars undergo core collapse explosions and what types of elements they produce, with stars more massive than approximately 8 solar masses ending as supernovae, while less massive stars complete their evolution as white dwarfs. This mass threshold helps explain the observed abundance patterns of heavy elements in galaxies and the chemical evolution of cosmic matter. The Type I supernovae that result from white dwarf explosions provide additional sources of iron peak elements while demonstrating alternative pathways for explosive nucleosynthesis that operate under different physical conditions than core collapse supernovae. These thermonuclear explosions create distinctive abundance patterns that complement the products of core collapse nucleosynthesis. Picture Type I supernovae as cosmic foundries specialized in iron production, with white dwarf stars undergoing complete thermonuclear disruption that converts carbon and oxygen into iron and nickel with remarkable efficiency. These explosions demonstrate how stellar death can take multiple forms while contributing different suites of elements to galactic chemical inventories. The hypernova explosions that characterize the most massive stellar deaths create even more extreme conditions for nucleosynthesis, while potentially producing the heaviest elements through R-process neutron capture occurring in environments with the highest possible neutron densities. These rare but energetic events may be responsible for creating significant fractions of the universe's gold, platinum, and uranium. The neutron star mergers that occur when binary neutron star systems spiral together through gravitational wave emission create additional sites for R-process nucleosynthesis, demonstrating that heavy element synthesis continues throughout cosmic history through rare but productive stellar collision events. These mergers may be responsible for approximately half of all elements heavier than iron. Tonight, As you settle into deeper rest, you can appreciate how supernova explosions represent moments of cosmic creativity that transform stellar death into elemental birth, converting the gravitational collapse of massive stars into the explosive synthesis and distribution of heavy elements that make rocky planets and complex chemistry possible. The moment of stellar transformation that occurs during supernova explosion demonstrates how the universe converts stellar endings into cosmic beginnings, ensuring that stellar nucleosynthesis continues, enriching the cosmos with the elements essential for planets, life, and the ongoing story of cosmic evolution. In the aftermath of supernova explosion, when the dramatic moment of stellar transformation has passed and a new neutron star settles into its exotic state of matter, the real work of cosmic enrichment begins as expanding shells of stellar debris carrying the accumulated products of millions of years of nucleosynthesis, plus the newly forged heavy elements from explosive burning sweep outward into the surrounding interstellar medium at speeds of thousands of miles per second. This expanding supernova remnant represents one of nature's most efficient distribution systems, spreading star-forged elements across vast regions of space where they will eventually seed new generations of star formation with the heavy elements essential for rocky planet formation and the complex chemistry that makes life possible. Picture this expanding supernova remnant as a spherical bubble of hot, glowing gas growing larger with each passing year, its boundaries marked by the collision between high-speed stellar ejecta and the tenuous matter that fills the spaces between stars. The shock waves created by this collision heat both the stellar debris and the ambient interstellar medium to temperatures of millions of degrees, creating conditions where atoms are completely ionized and the gas glows brilliantly across the electromagnetic spectrum from radio waves to gamma rays. The initial expansion phase of supernova remnants proceeds with remarkable violence as stellar ejecta, traveling at 10,000 miles per second or more, sweeps up interstellar matter and accelerates it to comparable speeds, creating shock fronts that propagate outward while gradually slowing as they encounter increasing amounts of ambient material. During this phase, which lasts several hundred years, the supernova remnant grows from a few light years to dozens of light years in diameter, while maintaining the high temperatures and rapid expansion that characterize young supernova remnants. As you breathe slowly and peacefully tonight, you can imagine these expanding shells of stardust spreading through the galaxy like ripples on a cosmic pond, each remnant carrying within its glowing boundaries a complete inventory of stellar nucleosynthesis: hydrogen and helium from the stellar atmosphere, carbon and oxygen from helium burning, silicon and iron from the stellar core, and gold and uranium from explosive R-process synthesis. This expanding matter represents the life's work of stellar nucleosynthesis being gently distributed throughout galactic space. The adiabatic expansion phase that follows the initial shock-dominated period allows supernova remnants to grow to hundreds of light years in diameter, while gradually cooling and slowing as they interact with larger volumes of interstellar matter. During this phase, which can last tens of thousands of years, the remnant transitions from a violently expanding shock front to a more gentle pressure wave that pushes against the surrounding interstellar medium while continuing to carry stellar nucleosynthetic products outward from their point of origin. Picture the supernova remnant during this mature phase as a vast, slowly expanding shell of warm gas enriched with heavy elements, no longer glowing brilliantly, but still detectable through radio emission and subtle heating of the surrounding interstellar medium. The stellar nucleosynthetic products distributed during this phase become incorporated into the general interstellar chemical inventory, available for eventual inclusion in new episodes of star formation. The mixing processes that occur as supernova ejecta interacts with ambient interstellar matter help homogenize the chemical composition of galactic gas, while preventing the formation of distinct chemical boundaries that might inhibit the incorporation of stellar nucleosynthetic products into future star formation. Turbulent mixing, Rayleigh-Taylor instabilities, and other fluid dynamic processes ensure that heavy elements become thoroughly distributed throughout expanding supernova remnants. The chemical enrichment created by supernova remnants proceeds gradually over thousands of years as stellar nucleosynthetic products mix with ambient interstellar matter, slowly increasing the heavy element content of galactic gas reservoirs while creating the chemical gradients that characterize galactic structure. Each supernova explosion enriches a region of space hundreds of light years in diameter with elements that were not present when the progenitor star first formed. Consider how the heavy elements distributed by supernova remnants include not only the products of peaceful stellar nucleosynthesis like carbon, oxygen, and iron, but also exotic elements like gold, platinum, and uranium that can be created only through explosive nucleosynthesis. These rare but important elements become available for incorporation into planetary systems through supernova distribution, eventually becoming components of technological materials and biological systems. The supernova-driven galactic fountains that result from multiple supernova explosions in regions of active star formation create large-scale circulation patterns that transport chemically enriched gas from galactic disks into galactic halos, while drawing metal-poor gas from intergalactic space back into star-forming regions. These circulation patterns help regulate galactic chemical evolution, while ensuring efficient mixing of stellar, nucleosynthetic products throughout galactic volumes. Picture these galactic fountains as vast circulation systems driven by supernova energy, lifting chemically enriched gas thousands of light years above galactic planes, while creating the complex, three-dimensional flow patterns that characterize interstellar medium dynamics. These fountain flows help prevent galactic gas from becoming chemically stratified, while facilitating the transport of heavy elements across large galactic distances. The stellar wind interaction that precedes supernova explosion often creates cavities in the interstellar medium that influence how supernova remnants expand and distribute their nucleosynthetic products. Massive stars lose substantial amounts of mass through stellar winds during their evolution, creating bubbles of hot, low-density gas that can focus supernova expansion in particular directions, while creating preferential pathways for element distribution. The superbubbles created when multiple massive stars and stellar associations undergo supernova explosions within relatively small regions of space and time create even larger structures that can transport stellar nucleosynthetic products across significant fractions of galactic disks. These superbubbles represent some of the most efficient mechanisms for large-scale element redistribution, capable of enriching vast galactic volumes with the products of stellar nucleosynthesis. Imagine networks of superbubbles created by successive generations of massive star formation and supernova explosion, with overlapping remnants creating complex structures that facilitate the transport of heavy elements across galactic distances while driving turbulence and circulation patterns that enhance mixing between different galactic gas components. The dust formation that occurs in cooling supernova ejecta creates solid particles of stellar nucleosynthetic products that can survive transport through the interstellar medium while serving as nucleation sites for future star and planet formation. Supernova dust includes refractory elements like carbon, silicon, and iron that condense into microscopic grains capable of preserving chemical signatures of explosive nucleosynthesis for billions of years. Picture these dust grains as microscopic time capsules carrying the chemical fingerprints of stellar nucleosynthesis across cosmic distances and through multiple episodes of star formation, eventually becoming incorporated into planetary systems, where they provide direct samples of ancient stellar processing. Some dust grains found in meteorites originated in supernova explosions that occurred billions of years ago. The radiative cooling that eventually dominates supernova remnant evolution allows the expanding ejecta to transition from hot, ionized plasma to cooler, neutral gas that can participate in normal interstellar medium processes, including molecular cloud formation and subsequent star formation. This cooling phase marks the final integration of stellar nucleosynthetic products into the galactic chemical inventory. The cosmic ray acceleration that occurs at supernova shock fronts creates high-energy particles that transport stellar nucleosynthetic products across even larger distances than the expanding remnants themselves. With cosmic ray nuclei carrying chemical signatures of supernova nucleosynthesis throughout galactic volumes and potentially even to intergalactic space. Consider how cosmic rays accelerated by supernova shocks include heavy nuclei created through stellar nucleosynthesis, with these high-energy particles capable of traveling thousands of light-years from their supernova origins while preserving isotopic signatures that provide evidence for explosive nucleosynthesis processes. Cosmic ray studies allow direct sampling of supernova nucleosynthetic products from throughout the galaxy. The magnetic field amplification that occurs during supernova shock propagation creates enhanced magnetic field strengths that influence cosmic ray acceleration and transport while affecting the dynamics of supernova remnant expansion. These amplified magnetic fields help confine cosmic rays near supernova remnants while creating the conditions necessary for efficient particle acceleration to high energies. The neutron star kicks that result from asymmetric supernova explosions can propel newly formed neutron stars through galactic space at speeds of hundreds of miles per second, potentially transporting stellar nucleosynthetic products embodied in neutron star material across significant galactic distances. These high-velocity neutron stars represent mobile repositories of stellar nuclear processing that continue dispersing heavy elements through their trajectories across galactic space. Picture neutron stars as cosmic cannonballs shot through galactic space by supernova explosions, each one carrying within its exotic matter the compressed essence of stellar nucleosynthesis, while potentially seeding distant galactic regions with heavy elements through interactions with the interstellar medium during their high-speed journeys. The population 2 star formation that occurs in regions enriched by early supernova explosions creates the first generation of stars containing heavy elements produced by stellar nucleosynthesis, marking the beginning of galactic chemical evolution and demonstrating how supernova element distribution enables the formation of chemically complex stellar populations. The observational signatures of supernova element distribution include enhanced abundances of specific isotopes in interstellar gas, dust grain compositions that reflect supernova nucleosynthesis, and chemical abundance patterns in stellar atmospheres that record the history of galactic enrichment through supernova explosions. The galactic chemical evolution driven by supernova element distribution proceeds through multiple generations of star formation and stellar death, gradually increasing the heavy element content of galactic matter, while creating the chemical complexity necessary for rocky planet formation and the development of carbon-based chemistry that enables life. The local bubble surrounding our solar system represents a region of space that has been excavated and enriched by supernova explosions occurring within the past few million years, demonstrating how supernova element distribution continues to influence the local galactic environment and the chemical composition of matter in our immediate cosmic neighborhood. Picture our solar system floating within this local bubble, surrounded by hot, tenuous gas that has been chemically enriched by recent supernova explosions while being protected from the more extreme conditions that characterize active supernova remnants. This bubble represents our immediate chemical heritage from stellar nucleosynthesis and supernova distribution processes. The ongoing supernova rate in galaxies like the Milky Way ensures continuous chemical enrichment through stellar element distribution, with approximately 1 supernova explosion occurring every 30 to 50 years and providing steady input of stellar nucleosynthetic products to galactic chemical inventories. The efficiency of supernova element distribution means that virtually all galactic matter has been processed through multiple generations of stellar nucleosynthesis, with even the most metal-poor stars containing trace amounts of heavy elements created by the first generation of massive stars and distributed through the earliest supernova explosions. Tonight, as you drift toward deeper rest, you can appreciate how the supernova remnants expanding throughout our galaxy continue the ancient work of distributing stellar nucleosynthetic products, scattering the stardust created through millions of years of stellar evolution and moments of explosive transformation across vast regions of space, where it will eventually become incorporated into new stellar and planetary systems. The elements flowing through your bloodstream tonight have traveled countless light years from their stellar birthplaces, carried by supernova winds across cosmic distances to eventually become part of the chemistry that enables your existence beneath the stars. Across the vast expanse of galactic space, the heavy elements scattered by countless supernova explosions begin their patient journey back into the cosmic cycle of star and planet formation, gathering slowly in the gravitational embrace of molecular clouds where hydrogen and helium mix with the star-forged carbon, oxygen, iron, and gold that will transform these new stellar nurseries into cosmic gardens capable of growing not just new generations of stars, but entire planetary systems rich in the chemical complexity that makes rocky worlds and eventually life itself possible. Picture the interstellar medium as a vast cosmic ocean enriched with the mineral wealth of stellar nucleosynthesis, where currents of gas and dust carry heavy elements across light years of space, while gravity slowly concentrates this chemically enriched matter into the dense molecular clouds that will become the birthplaces of chemically complex stellar and planetary systems. These molecular clouds represent cosmic recycling centers where the death of ancient stars becomes the raw material for new cosmic creativity. The gravitational collapse that initiates new episodes of star formation now operates on matter that contains a much richer chemical inventory than the primordial hydrogen and helium that characterize the universe's first stellar generation. Modern molecular clouds contain carbon dust grains that can serve as nucleation sites for more complex molecular chemistry, oxygen that can combine with hydrogen to form water ice, and iron that can condense into metallic particles that will eventually become the cores of rocky planets. As you breathe slowly and naturally tonight, you can imagine these molecular clouds as cosmic workshops, where the scattered products of stellar nucleosynthesis begin organizing themselves according to gravitational and chemical forces that will determine the architecture of new stellar and planetary systems. The same carbon atoms that were forged in the hearts of ancient stars now participate in the complex organic chemistry occurring in molecular cloud environments. The dust grain chemistry that occurs within molecular clouds provides surfaces where hydrogen atoms can combine to form molecular hydrogen, while enabling more complex chemical reactions that create water, carbon monoxide, methanol, and even amino acids in the cold depths of interstellar space. These dust grains, many of which originated as stellar nucleosynthetic products in supernova explosions or stellar winds, serve as cosmic laboratories for developing the chemical complexity that will characterize planetary systems. Picture these microscopic dust grains floating in the near vacuum of molecular clouds, each one potentially carrying stellar nucleosynthetic products, while serving as a tiny chemical factory where simple molecules combine to form more complex compounds. The surface chemistry occurring on these grains helps build the molecular inventory that will eventually become incorporated into new stellar and planetary systems. The gravitational instabilities that trigger star formation in chemically enriched molecular clouds create protostars surrounded by accretion disks that contain not only hydrogen and helium, but significant quantities of heavier elements that can condense into solid particles at the relatively low temperatures found in the outer regions of these protoplanetary systems. This solid material provides the building blocks for rocky planet formation through gravitational accumulation. The temperature and pressure gradients that develop in protoplanetary disks create distinct zones where different stellar nucleosynthetic products can condense into solid form, with refractory elements like calcium and aluminum condensing close to the central protostar, while more volatile elements like oxygen and carbon remain in gaseous form until temperatures drop sufficiently in the outer disk regions for ice formation and organic compound condensation. Consider how the chemical composition of protoplanetary disks reflects the integrated history of stellar nucleosynthesis in the galactic region where star formation occurs, with disk chemistry recording the accumulated contributions of hydrogen burning, helium burning, carbon burning, silicon burning, and explosive nucleosynthesis from multiple generations of stellar evolution and death. The planetary accretion process that builds rocky planets from solid material in protoplanetary disks incorporates stellar nucleosynthetic products directly into planetary structure, with iron from stellar cores becoming planetary cores, silicon and oxygen from helium burning, forming silicate mantles and crusts, and trace amounts of heavy elements from explosive nucleosynthesis becoming components of planetary atmospheres and surface materials. Picture the gradual accumulation of solid particles in protoplanetary disks as gravity organizes stellar nucleosynthetic products into larger and larger aggregations. From microscopic dust grains to pebbles to asteroids to planetary embryos to full planets. Each stage of accretion incorporating more stellar nuclear processing products into growing planetary systems while preserving chemical signatures of ancient stellar nucleosynthesis. The differentiation processes that occur as planets grow large enough for internal heating help organize stellar nucleosynthetic products according to their chemical and physical properties, with dense iron peak element from stellar cores sinking toward planetary centers, while lighter silicate materials from stellar helium burning rise to form planetary mantles and crusts. The atmospheric formation that accompanies rocky planet development incorporates volatile stellar nucleosynthetic products, including carbon, nitrogen, and oxygen that outgas from planetary interiors or arrive through cometary bombardment, creating atmospheric compositions that reflect both stellar nuclear processing and subsequent planetary chemical evolution. Imagine planetary atmospheres as repositories of stellar nucleosynthesis, where carbon dioxide from stellar helium burning, nitrogen from stellar carbon burning, and water vapor from hydrogen and oxygen created in stellar cores combine to create the chemical environments that make complex atmospheric chemistry possible while preserving isotopic signatures of stellar nuclear processing. The cometary delivery of stellar nucleosynthetic products to planetary surfaces provides additional mechanisms for incorporating the chemical diversity created by stellar evolution into planetary environments, with comets serving as cosmic delivery vehicles that transport volatile compounds from the outer regions of stellar systems to the inner zones where rocky planets can utilize these materials for atmospheric and surface chemistry. The late heavy bombardment that characterizes early planetary system evolution helps mix stellar nucleosynthetic products throughout planetary systems while delivering additional quantities of heavy elements to planetary surfaces through asteroid and comet impacts. This bombardment period represents a final phase of planetary accretion that ensures thorough chemical mixing of stellar nuclear processing products throughout planetary environments. Picture this bombardment period as a time of intensive chemical delivery when stellar nucleosynthetic products accumulated over billions of years of galactic evolution were being concentrated and organized into planetary systems, creating the chemical foundations that would eventually enable complex geological processes and potentially biological evolution. The hydrothermal chemistry that develops in planetary environments provides settings where stellar nucleosynthetic products can participate in complex chemical reactions under conditions of elevated temperature and pressure, creating environments where organic chemistry can develop complexity far beyond what occurs in interstellar space, while utilizing elements created through stellar nuclear processing. The geological processes that operate on rocky planets help concentrate and organize stellar nucleosynthetic products through igneous activity, sedimentary processes, and metamorphic transformation, creating mineral deposits and chemical concentrations that reflect the original stellar sources while enabling the development of diverse planetary surface environments. Consider how mountain building, volcanic activity, and plate tectonics help distribute stellar nucleosynthetic products throughout planetary environments, while creating the geological diversity that characterizes chemically complex planetary systems. These processes ensure that elements created in stellar cores become accessible for surface chemistry and potentially biological utilization. The magnetic field generation that occurs in planetary cores, composed of iron from stellar nucleosynthesis, creates protective magnetospheres that shield planetary surfaces from cosmic radiation while preserving atmospheric compositions that depend on stellar nuclear processing products. These magnetic fields help maintain the environmental stability necessary for complex chemistry and potentially life. The chemical evolution that occurs in planetary atmospheres and surface environments operates on stellar nucleosynthetic products through photochemistry, aqueous chemistry, and gas phase reactions that can create complex organic compound from simple precursors, demonstrating how stellar nuclear processing provides the raw materials for increasingly complex chemistry in planetary environments. Picture planetary atmospheres as vast chemical laboratories where carbon, nitrogen, and oxygen from stellar nucleosynthesis participate in photochemical reactions driven by stellar energy, creating increasingly complex molecular compounds while preserving chemical signatures that connect planetary chemistry to ancient stellar nuclear processing. The isotopic signatures preserved in meteorites and planetary materials provide detailed records of stellar nucleosynthesis, while demonstrating how stellar nuclear processing products become incorporated into planetary systems, with isotopic anomalies serving as fingerprints of specific stellar sources and nucleosynthetic processes. The presolar grain populations found in primitive meteorites include actual stellar nucleosynthetic products that survive planetary system formation while preserving chemical and isotopic signatures of specific stellar sources, providing direct samples of stellar nuclear processing that can be studied in terrestrial laboratories. Consider how these presolar grains represent cosmic time capsules that carry the direct products of stellar nucleosynthesis across billions of years and thousands of light years, to eventually become incorporated into planetary systems, where they provide tangible connections to ancient stellar evolution and death. The organic chemistry that develops in chemically enriched planetary environments utilizes carbon, nitrogen, and oxygen from stellar nucleosynthesis to create increasingly complex molecular systems that demonstrate the creative potential of stellar nuclear processing products when they become available for complex chemistry in planetary settings. The prebiotic chemistry that may develop in planetary environments rich in stellar nucleosynthetic products creates conditions where complex organic compounds can form spontaneously while utilizing elements created through stellar evolution, potentially setting the stage for the emergence of biological systems that represent the ultimate expression of stellar nuclear creativity. Picture prebiotic chemical environments where carbon from stellar helium burning, nitrogen from stellar carbon burning, and phosphorus from stellar oxygen burning combine under planetary conditions to create complex organic molecules that preserve within their structure the chemical signatures of ancient stellar nucleosynthesis, while potentially enabling the emergence of self-replicating chemistry. The ongoing accretion of interstellar material by planetary systems ensures continued delivery of stellar nucleosynthetic products throughout planetary system evolution, maintaining chemical connections between planetary environments and the ongoing cosmic cycle of stellar evolution and galactic chemical enrichment. The stellar system formation that continues throughout galactic evolution demonstrates how cosmic recycling operates as a continuous process, with each new generation of stellar and planetary systems incorporating increasing quantities of stellar nucleosynthetic products while contributing to ongoing galactic chemical evolution through continued stellar nuclear processing. Tonight, as you settle deeper into rest, you can appreciate how the cosmic recycling of stellar nucleosynthetic products continues throughout our galaxy, transforming the scattered ashes of ancient stars into the chemical foundations for new stellar and planetary systems, while ensuring that the creative work of stellar nucleosynthesis becomes available for increasingly complex cosmic chemistry. The elements that will someday become part of distant planetary systems and potentially support life on worlds not yet formed are currently being organized through cosmic recycling processes that connect stellar death to cosmic renewal through the patient work of gravitational collapse and chemical organization. Floating peacefully through space in the outer reaches of an ordinary spiral galaxy, our small blue planet carries within its rocky interior, swirling atmosphere, and vast oceans a complete inventory of stellar nucleosynthesis that represents the accumulated creative work of countless generations of stars that lived, evolved, and died over billions of years before our solar system even began to form. Every atom in Earth's structure tells a story of stellar fusion, explosive nucleosynthesis, and cosmic distribution that connects our world directly to the ancient furnaces where elements were forged and the supernova explosions that scattered stellar products across the galaxy to eventually become incorporated into the molecular cloud that would give birth to our sun and planets. Picture Earth as a cosmic archive that preserves within its geological layers, atmospheric composition, and oceanic chemistry a detailed record of galactic chemical evolution, with each element representing a specific stellar process and nucleosynthetic pathway that operated in stars whose light faded billions of years before our planet existed. The iron in Earth's core was forged in stellar cores through silicon burning. The oxygen in our atmosphere was created through helium fusion in stellar interiors, and the carbon in Earth's rocks and life forms originated in the hearts of ancient red giant stars. The formation of our solar system approximately 4.5 billion years ago occurred within a molecular cloud that had been enriched by millions of years of stellar evolution and supernova explosions, creating a chemical environment that contained approximately 2% heavy elements by mass. Enough stellar nucleosynthetic products to build rocky planets, create complex atmospheres, and eventually support the carbon-based chemistry that characterizes terrestrial life. As you breathe slowly and peacefully tonight, you can appreciate how the molecular cloud that gave birth to our solar system represented a cosmic treasure trove of stellar nucleosynthetic products, with dust grains carrying carbon from stellar helium burning, ice mantles containing oxygen and nitrogen from stellar cores, and trace amounts of gold, platinum, and uranium created during our process nucleosynthesis in supernova explosions and neutron star mergers. The accretion disk that surrounded the young sun contained stellar nucleosynthetic products organized by temperature and distance from the central star, with refractory elements like aluminum and calcium condensing in the inner solar system, where they became incorporated into the rocky planets, while volatile compounds containing carbon, nitrogen, and oxygen remained in gaseous form until they reached the outer regions where they could condense into ices and organic compounds. Picture the early solar system as a cosmic construction site where stellar nucleosynthetic products sorted themselves according to their physical and chemical properties, with iron from stellar cores gathering in the inner solar system to form planetary cores, silicate materials from stellar oxygen and silicon burning creating rocky planetary crusts and mantles, and volatile stellar products forming the atmospheres and surface ices that would later become essential for geological and biological processes. The planetary differentiation that occurred as Earth grew through accretion helped organize stellar nucleosynthetic products according to their density and chemical affinity, with the heaviest stellar products, iron and nickel from stellar cores, sinking toward Earth's center to form the metallic core that generates our planet's protective magnetic field, while lighter stellar products rose toward the surface to form the silicate mantle and crust where geological processes could organize them into diverse mineral formations. The early bombardment period that characterized Earth's first billion years delivered additional stellar nucleosynthetic products to our planet's surface through asteroid and comet impacts, bringing volatile compounds from the outer solar system that contain carbon, nitrogen, and water formed from stellar hydrogen and oxygen. This bombardment helped establish Earth's atmospheric composition while delivering the chemical diversity needed for complex surface chemistry. Imagine early Earth as a world actively receiving deliveries of stellar nucleosynthetic products through cosmic impacts, with each asteroid and comet bringing additional samples of stellar nuclear processing, while contributing to the growing chemical complexity that would eventually enable the development of oceans, atmospheres, and geological systems capable of supporting life. The outgassing processes that occurred as Earth's interior heated during accretion released volatile stellar nucleosynthetic product from planetary rocks, creating the early atmosphere that contained carbon dioxide from stellar carbon, nitrogen from stellar nuclear processing, and water vapor from hydrogen and oxygen created in stellar cores. This atmosphere represented the first concentration of stellar products in Earth's surface environment. The ocean formation that occurred as water vapor condensed from the early atmosphere created vast reservoirs of stellar nucleosynthetic products in liquid form, with seawater containing dissolved ions of sodium, magnesium, calcium, and chlorine that originated in stellar nuclear processing, while providing the aqueous environment where complex chemistry could develop using elements created in stellar interiors. Picture Earth's early oceans as vast solutions of stellar nucleosynthetic products, with every dissolved ion representing elements created through specific stellar processes: sodium from stellar carbon burning, magnesium from stellar oxygen burning, calcium from stellar silicon burning, all brought together in liquid water formed from stellar hydrogen and oxygen to create the chemical environment where terrestrial chemistry could begin exploring the creative potential of stellar nuclear processing. The geological evolution that has characterized Earth throughout its history represents an ongoing process of organizing and concentrating stellar nucleosynthetic products through igneous processes, metamorphic transformation, and sedimentary concentration that create the mineral diversity and chemical complexity that characterize modern terrestrial environments. The plate tectonic processes that drive Earth's geological activity help circulate stellar nucleosynthetic products between Earth's interior and surface, while creating the geological diversity that concentrates different stellar products in different environments. Volcanic activity brings deep Earth stellar products to the surface, while subduction carries surface stellar products back into the mantle, where they can be reprocessed through high-temperature geological chemistry. Consider how every geological process on Earth operates using stellar nucleosynthetic products as raw materials, with mountain building concentrating stellar aluminum and silicon, volcanic activity distributing stellar iron and magnesium, and sedimentary processes organizing stellar carbon and calcium into concentrated deposits that preserve records of Earth's chemical evolution. The atmospheric evolution that has occurred throughout Earth's history reflects the ongoing interaction between stellar nucleosynthetic products and biological processes, with atmospheric oxygen increasing through photosynthesis that utilizes stellar carbon and hydrogen, while atmospheric carbon dioxide varies through geological processes that involve stellar calcium and magnesium in rock weathering and formation. The magnetic field generation that occurs in Earth's iron-nickel core provides protection for surface environments while demonstrating how stellar nucleosynthetic products from ancient stellar cores continue performing essential functions for planetary habitability. The iron that generates Earth's magnetic field was created through silicon burning in massive stellar cores billions of years ago. Picture Earth's magnetic field as a protective bubble generated by stellar nucleosynthetic products, with iron and nickel created in ancient stellar cores now flowing in Earth's outer core to create the dynamo processes that shield our planet from cosmic radiation while preserving the atmospheric composition needed for complex surface chemistry and life. The hydrological cycle that circulates water through Earth's surface environments operates using hydrogen and oxygen created in stellar cores, while transporting dissolved stellar nucleosynthetic products through terrestrial environments, creating the chemical transport systems that enable complex geological and biological chemistry throughout Earth's surface environments. The soil formation processes that create Earth's agricultural foundation represent complex interactions between stellar nucleosynthetic products and biological systems, with soil chemistry depending on stellar silicon, aluminum, iron, and calcium, while soil organic matter incorporates stellar carbon and nitrogen through biological processing that demonstrates the integration of stellar nuclear processing with terrestrial life. The mineral formation that characterizes Earth's geological diversity creates concentrated deposits of specific stellar nucleosynthetic products through hydrothermal processes, metamorphic transformation, and igneous crystallization that organize stellar elements into the diverse mineral structures that provide raw materials for geological processes and eventually technological applications. Picture Earth's mineral wealth as organized collections of stellar nucleosynthetic products, with copper deposits containing stellar elements from explosive nucleosynthesis, quartz formations built from stellar silicon and oxygen, and limestone formations incorporating stellar carbon and calcium that demonstrate how geological processes can concentrate and organize the scattered products of ancient stellar nucleosynthesis. The rare earth element deposits that provide essential materials for modern technology contain stellar nucleosynthetic products created through our process nucleosynthesis during supernova explosions and neutron star mergers, demonstrating how even the most exotic stellar nuclear processing products have become essential components of terrestrial technology and industrial applications. The radioactive decay that provides energy for Earth's geological processes utilizes long-lived isotopes created during stellar nucleosynthesis, with uranium and thorium from our process nucleosynthesis powering plate tectonics and maintaining Earth's geological activity over billions of years while preserving isotopic signatures that record the timing and sources of stellar nuclear processing. Consider how Earth's internal heat engine operates using stellar nucleosynthetic products, with radioactive decay of stellar uranium, thorium, and potassium providing the energy that drives convection in Earth's mantle while maintaining the geological activity that creates Earth's surface diversity and supports the dynamic processes that make our planet habitable. The atmospheric chemistry that characterizes modern Earth operates using stellar nucleosynthetic products through photochemical processes that utilize stellar carbon, nitrogen, and oxygen, while creating complex atmospheric compositions that reflect both stellar nuclear processing and biological modification of stellar products through photosynthesis and respiration. The chemical weathering that breaks down Earth's rocks represents ongoing interaction between stellar nucleosynthetic products and surface environments, with stellar silicon, aluminum, and iron being dissolved and transported through hydrological systems, while contributing to soil formation and oceanic chemistry that depends entirely on stellar nuclear processing products. The carbon cycle that regulates Earth's climate operates using stellar carbon through geological and biological processes that demonstrate how stellar nucleosynthetic products can be organized into complex regulatory systems that maintain environmental stability over geological timescales while supporting the chemical complexity that characterizes terrestrial life. Picture the global carbon cycle as a vast circulation system that moves stellar carbon between Earth's atmosphere, oceans, rocks, and living systems while maintaining the chemical balance that supports life, with every carbon atom participating in this cycle representing stellar nucleosynthesis that occurred in ancient red giant stars before a solar system existed. The nitrogen cycle that supports terrestrial biology operates using stellar nitrogen through atmospheric, geological, and biological processes that make stellar nuclear processing products available for biological utilization, while demonstrating how stellar nucleosynthesis creates the chemical foundations for complex ecological systems. The phosphorus cycle that enables biological energy storage and genetic information transfer utilizes stellar phosphorus created through stellar oxygen burning, while demonstrating how even relatively rare stellar nucleosynthetic products can become essential components of biological systems through concentration and organization in terrestrial environments. The technological applications that characterize human civilization depend entirely on stellar nucleosynthetic products, with every manufactured material representing organized stellar and nuclear processing products that have been concentrated, purified, and modified through technological processes that demonstrate human ability to utilize the chemical diversity created through billions of years of stellar evolution. Tonight, as you settle into deeper rest, you can appreciate how Earth represents a living museum of stellar nucleosynthesis where every geological formation, atmospheric component, and oceanic constituent preserves evidence of ancient stellar nuclear processing while participating in ongoing terrestrial processes that organize stellar products into increasingly complex chemical and physical systems. Our planet serves as both a repository of stellar nuclear creativity and a laboratory where stellar nucleosynthetic products continue exploring their potential for creating complexity, beauty, and eventually the chemical foundations that make life possible. Within the countless trillions of cells that compose your body as you rest peacefully tonight flows an intricate symphony of stellar nucleosynthetic products that have been organized through billions of years of biological evolution into the molecular machinery of life itself, with every protein, enzyme, and genetic molecule representing a sophisticated arrangement of carbon, nitrogen, oxygen, phosphorus, and sulfur that were forged in the nuclear furnaces of ancient stars and scattered across the galaxy to eventually become the chemical foundation for consciousness, memory, and a remarkable phenomenon of biological complexity that characterizes life on Earth. Picture the molecular landscape within a single living cell as a bustling metropolis constructed entirely from stellar nucleosynthetic products, where carbon atoms created through helium burning in red giant stars form the backbone of every organic molecule. Oxygen from stellar cores enables the energy-releasing reactions of cellular respiration. Nitrogen from stellar nuclear processing builds the amino acids that fold into functional proteins, and phosphorus from stellar oxygen burning creates the energy storage molecules that power all cellular activities. The DNA molecules that carry genetic information within your cells represent perhaps the most elegant utilization of stellar nucleosynthetic products in biological systems. With the double helix structure built from carbon and nitrogen created in stellar cores, while the phosphate backbone incorporates phosphorus from stellar nucleosynthesis, and the hydrogen bonding that holds the structure together utilizes hydrogen, created in the first few minutes after the Big Bang, combined with stellar nitrogen and oxygen. As you breathe slowly and naturally tonight, you can appreciate how each breath incorporates stellar oxygen into your bloodstream, while removing stellar carbon dioxide, creating a continuous exchange of stellar nucleosynthetic products between your body and the atmosphere that demonstrates the ongoing circulation of stellar elements through biological systems and connects your metabolism directly to the ancient stellar processes that created the elements enabling life. The hemoglobin molecules that transport oxygen through your bloodstream contain iron atoms created through silicon burning in massive stellar cores, with each iron atom serving as the active site that binds oxygen molecules and enables their transport from lungs to tissues throughout your body. This iron, forged in stellar furnaces billions of years ago, now performs the essential biological function of oxygen transport that makes complex multicellular life possible. Picture these hemoglobin molecules as tiny molecular vehicles carrying stellar oxygen through your bloodstream, with iron from ancient stellar cores serving as the binding site that enables oxygen transport, while demonstrating how stellar nucleosynthetic products can be incorporated into sophisticated biological machinery that performs functions essential for life. The protein enzymes that catalyze biochemical reactions throughout your body utilize stellar nucleosynthetic products in remarkably specific ways, with enzyme active sites often containing metal atoms like zinc, copper, or manganese created through stellar nuclear processing, while the protein structures that position these metal atoms precisely are built from amino acids containing stellar carbon, nitrogen, and sulfur arranged in complex three-dimensional configurations. The calcium ions that regulate cellular processes and provide structural support for bones and teeth represent stellar nucleosynthetic products from silicon burning in massive stars, now organized into biological systems that enable muscle contraction, nerve signal transmission, and the mechanical support that makes complex multicellular organisms possible. Consider how the sodium and potassium ions that generate electrical signals in nerve cells represent stellar nucleosynthetic products that have been incorporated into biological systems for information processing and communication, with stellar elements creating the electrochemical gradients that enable neural activity, memory formation, and the consciousness that allows you to contemplate your stellar origins. The chlorophyll molecules that enable photosynthesis contain magnesium atoms created through stellar oxygen burning, allowing plants to capture solar energy and convert stellar carbon dioxide into organic compounds while releasing stellar oxygen back to the atmosphere. This process demonstrates how stellar nucleosynthetic products enable the energy capture and conversion that forms the foundation of terrestrial food webs. Picture photosynthesis as a biological process that utilizes stellar nucleosynthetic products to capture stellar energy, with magnesium from ancient stellar cores enabling chlorophyll to absorb sunlight while converting atmospheric carbon dioxide from stellar sources into the organic molecules that provide energy for virtually all life on Earth. The ADP molecules that store and transfer energy in biological systems represent sophisticated arrangements of stellar nucleosynthetic products, with adenine containing nitrogen from stellar nuclear processing, ribose built from stellar carbon and oxygen, and the phosphate groups incorporating phosphorus from stellar oxygen burning, all organized into molecular structures that enable efficient energy storage and transfer in living systems. The cellular membranes that define cell boundaries and regulate molecular transport utilize phospholipids containing stellar carbon, nitrogen, and phosphorus arranged in bilayer structures that demonstrate how stellar nucleosynthetic products can self-organize into complex molecular architectures that enable cellular compartmentalization and the regulation of biochemical processes. Imagine cellular membranes as sophisticated molecular filters built from stellar nucleosynthetic products, with phospholipid molecules containing stellar carbon and phosphorus organizing themselves into structures that control which molecules can enter or leave cells while maintaining the chemical gradients necessary for cellular energy production and information processing. The nucleotide bases that encode genetic information represent elegant molecular arrangements of stellar carbon and nitrogen that demonstrate how stellar nucleosynthetic products can be organized into information storage systems capable of preserving and transmitting the instructions for building complex biological structures across generations. The ribosome complexes that synthesize proteins utilize stellar nucleosynthetic products in RNA molecules that catalyze peptide bond formation while organizing amino acids containing stellar carbon, nitrogen, and sulfur into functional protein structures, demonstrating how stellar elements enable the molecular machinery that builds biological complexity. Picture ribosomes as molecular factories built from stellar nucleosynthetic products, with RNA containing stellar carbon, nitrogen, and phosphorus serving as both structural components and catalytic elements that enable the synthesis of proteins from amino acids containing additional stellar carbon, nitrogen, and sulfur. The vitamin and cofactor molecules that enable enzyme function often contain trace amounts of stellar nucleosynthetic products like cobalt, molybdenum, and selenium created through our process nucleosynthesis during supernova explosions, demonstrating how even the rarest stellar nuclear processing products can become essential components of biological systems through concentration and organization in living organisms. The collagen fibers that provide structural support throughout your body represent organized arrangements of stellar carbon, nitrogen, and oxygen that demonstrate how stellar nucleosynthetic products can be assembled into materials with remarkable mechanical properties that enable the structural integrity of complex multicellular organisms. Consider how the keratin proteins that form hair, skin, and nails utilize stellar carbon, nitrogen, and sulfur in molecular structures that provide protection and mechanical support, while demonstrating the versatility of stellar nucleosynthetic products for creating diverse biological materials with specialized functions. The neurotransmitter molecules that enable communication between nerve cells represent sophisticated arrangements of stellar nucleosynthetic products that demonstrate how stellar carbon, nitrogen, and oxygen can be organized into signaling molecules that enable complex nervous system function and the neural processes underlying consciousness and memory. Picture neurotransmitters as molecular messengers built from stellar nucleosynthetic products, with molecules like serotonin and dopamine containing stellar carbon and nitrogen organized into structures that enable chemical communication between neurons while contributing to the neural activities that create thoughts, emotions, and consciousness. The immune system molecules that protect your body from pathogens utilize stellar nucleosynthetic products in antibody proteins and cytokine signaling molecules that demonstrate how stellar elements enable biological defense systems while preserving the chemical and structural integrity necessary for continued life and health. The hormonal regulation systems that coordinate biological activities throughout your body depend on stellar nucleosynthetic products and hormone molecules that travel through your bloodstream to regulate growth, metabolism, and reproduction, while demonstrating how stellar elements enable the complex coordination necessary for multicellular organism function. The metabolic pathways that extract energy from food and synthesize essential biological molecules represent sophisticated networks of biochemical reactions that utilize stellar nucleosynthetic products as both reactants and catalysts, while demonstrating the remarkable efficiency with which biological systems can organize stellar elements to support life processes. Picture cellular metabolism as a complex network of chemical reactions that process stellar nucleosynthetic products to extract energy and build essential molecules. With every step in glycolysis, cellular respiration, and biosynthetic pathways utilizing carbon, nitrogen, oxygen, and phosphorus created in ancient stellar cores. The sensory systems that allow you to perceive the world around you utilize stellar nucleosynthetic products and rhodopsin molecules that enable vision, olfactory receptors that detect chemical signals, and mechanosensitive channels that respond to physical stimuli, all demonstrating how stellar elements enable biological perception and the neural processing that creates conscious experience. The reproductive systems that enable biological continuity utilize stellar nucleosynthetic products in gamete formation, embryonic development, and the molecular machinery that maintains genetic information across generations, while demonstrating how stellar elements enable the biological processes that ensure life continues, exploring the creative potential of stellar nuclear processing. The aging processes that characterize biological systems involve the gradual accumulation of molecular damage to stellar nucleosynthetic products organized in biological structures, with oxidative damage affecting stellar carbon and nitrogen in proteins and DNA, while demonstrating how stellar elements experience wear and recycling even within biological systems. Consider how the biological recycling that occurs through death and decomposition returns stellar nucleosynthetic products to environmental circulation, with bacterial and fungal decomposition breaking down complex biological molecules to release stellar carbon, nitrogen, and phosphorus back to soil and atmospheric systems where they become available for continued biological utilization. The evolutionary processes that have shaped life on Earth represent ongoing exploration of the organizational potential of stellar nucleosynthetic products, with natural selection favoring biological systems that can utilize stellar elements more efficiently, while creating increasingly complex and sophisticated arrangements of stellar nuclear processing products in living systems. The consciousness that allows you to contemplate these stellar connections represents perhaps the most remarkable achievement of stellar nucleosynthesis, with neural networks built from stellar carbon, nitrogen, and oxygen creating the information processing systems that enable self-awareness, abstract thought, and the ability to understand your own cosmic origins through scientific investigation. Picture consciousness as the universe becoming aware of itself through stellar nucleosynthetic products organized into neural networks, with thoughts and memories representing patterns of activity in biological systems built entirely from elements created in ancient stellar cores, demonstrating how stellar nuclear processing eventually enables the universe to contemplate its own creative processes. The technological extensions of biological capabilities utilize stellar nucleosynthetic products in electronic devices, transportation systems, and communication networks that expand human sensory and cognitive abilities, while demonstrating how biological systems can organize stellar elements to create tools that further enhance the creative potential of stellar nuclear processing products. The medical technologies that extend and improve biological function represent sophisticated applications of stellar nucleosynthetic products in pharmaceutical compounds, medical devices, and therapeutic procedures that demonstrate how understanding stellar nuclear processing can enable more effective utilization of stellar elements for maintaining and enhancing biological health. Tonight, as you drift toward deeper rest, you can appreciate how every biological process occurring in your body represents a sophisticated utilization of stellar nucleosynthetic products that connects your existence directly to ancient stellar evolution, while demonstrating the remarkable creativity that emerges when stellar nuclear processing products become organized into the complex molecular machinery of life. Your consciousness, memory, and dreams all depend on stellar elements arranged in neural networks that enable the universe to experience itself through the biological utilization of cosmic nucleosynthesis. As our gentle journey through the cosmic story of element creation draws toward its peaceful conclusion, we arrive at perhaps the most profound and beautiful truth that science has ever revealed about our place in the universe: that you are not separate from the cosmos, but are instead an intimate part of it. With every atom in your body representing a direct connection to ancient stellar processes that forged the elements of life in nuclear furnaces scattered across space and time. The carbon in your muscles, the iron in your blood, the calcium in your bones, and the oxygen you breathe all carry within their atomic structure the history of stellar evolution, supernova explosions, and cosmic recycling that makes you not just an observer of the universe, but a living embodiment of cosmic creativity itself. Picture yourself not as a temporary arrangement of matter separate from the vast cosmos, but as a local concentration of stellar nucleosynthetic products that has achieved the remarkable feat of self-awareness, consciousness, and the ability to contemplate the very stellar processes that created the elements, making such contemplation possible. You're quite literally made of star stuff, organized through billions of years of cosmic evolution into a form capable of understanding and appreciating the elegant nuclear alchemy that forged your atomic constituents in stellar cores that burned bright billions of years before Earth existed. The elements flowing through your bloodstream at this very moment began their journey in the hearts of massive stars that underwent the complete sequence of stellar nucleosynthesis, from hydrogen burning that created the helium in your body, through carbon burning that forged the neon and magnesium in your cells, to silicon burning that created the iron atoms now carrying oxygen through your circulatory system. Each of these elements carries within its nuclear structure the memory of extreme temperatures, crushing pressures, and the patient nuclear transformations that characterize stellar evolution. As you breathe slowly and peacefully tonight, you participate in an ancient cosmic circulation that connects you directly to ongoing stellar processes throughout the galaxy, with each exhalation releasing carbon dioxide containing carbon atoms that were created in stellar cores, while each inhalation brings oxygen that was forged through helium fusion in red giant stars and distributed through space by stellar winds and supernova explosions before eventually becoming part of Earth's atmosphere, and now part of your own biological processes. The remarkable fact that you can understand your stellar origins through scientific investigation represents perhaps the most extraordinary achievement of cosmic evolution. The universe has evolved to the point where stellar nucleosynthetic products organized into biological systems can comprehend the nuclear processes that created them, turning the cosmos into a self-aware entity capable of studying its own creative mechanisms through the consciousness that emerges from appropriately organized stellar elements. Picture this as the universe waking up to itself through your awareness, with neural networks built from stellar carbon, nitrogen, and oxygen creating the information processing systems that enable cosmic self-recognition and understanding, demonstrating how stellar nucleosynthesis eventually produces not just chemical complexity, but also consciousness, memory, and the capacity for wonder that allows you to appreciate your cosmic heritage. The ongoing stellar nucleosynthesis occurring in stars throughout our galaxy continues creating new elements even as you rest tonight, with stellar cores throughout the Milky Way burning hydrogen into helium, fusing helium into carbon and oxygen, and building heavier elements through the nuclear processes we have explored together. This means you are connected not just to ancient stellar processes, but to ongoing cosmic creativity that continues enriching the universe with heavy elements while ensuring that future generations of stars and planets will have access to even greater chemical complexity. The supernova explosions that occur approximately once every 30 to 50 years in our galaxy continue distributing stellar nucleosynthetic products throughout space, scattering newly forged elements that will eventually become incorporated into future stellar and planetary systems where they may contribute to the development of complexity, chemistry, and potentially life forms that we cannot yet imagine, but which will share your fundamental stellar heritage. Consider how your existence represents both an endpoint and a beginning in cosmic evolution. An endpoint in the sense that you embody billions of years of stellar nucleosynthesis, cosmic distribution, and planetary evolution, but also a beginning in the sense that human consciousness and technology enable new forms of cosmic creativity that can purposefully organize stellar nucleosynthetic products in ways that natural processes alone might not achieve. The technological civilization that humanity has developed represents a new phase in the cosmic utilization of stellar nucleosynthetic products, with human intelligence and creativity enabling the organization of stellar elements into computers, spacecraft, communication systems, and scientific instruments that extend the universe's capacity for self-understanding while demonstrating how biological systems can become active participants in cosmic evolution rather than passive products of natural selection. The space exploration that carries human consciousness and technology beyond Earth represents stellar nucleosynthetic products returning to space in organized forms, with spacecraft built from stellar aluminum, iron, and silicon carrying human intelligence toward other worlds while potentially beginning the process of distributing Earth-based life and consciousness throughout the cosmos as active agents of further cosmic evolution. Picture spacecraft as vehicles that carry stellar nucleosynthetic products organized into technological systems beyond their planetary birthplace, potentially enabling the spread of consciousness and complexity to other worlds where stellar elements could be organized into new forms of creativity and awareness that continue exploring the potential of cosmic nucleosynthesis. The search for extraterrestrial life represents an attempt to discover whether stellar nucleosynthetic products have achieved self-organization into biological and potentially conscious systems elsewhere in the universe. Recognizing that any life we might discover would share our fundamental stellar heritage, while potentially demonstrating alternative pathways for organizing cosmic nucleosynthesis into complex, creative systems. The potential for communication with extraterrestrial intelligence would represent contact between different local concentrations of stellar nucleosynthetic products that have achieved consciousness and technological capability, creating opportunities for sharing discoveries about cosmic evolution while demonstrating the universe's capacity for producing multiple independent forms of self-awareness through appropriately organized stellar elements. Consider the profound implication that any extraterrestrial civilizations we might encounter would be composed of the same stellar nucleosynthetic products that compose us, having achieved consciousness through alternative organizational pathways, but sharing our fundamental cosmic heritage and connection to ancient stellar nuclear processing. Such contact would represent the universe recognizing itself through multiple independent forms of consciousness. The future evolution of human civilization may enable more sophisticated utilization of stellar nucleosynthetic products through advanced technology, genetic engineering, and potentially the development of artificial intelligence systems that extend consciousness beyond biological limitations, while continuing to explore the creative potential of stellar nuclear processing in ways that biological evolution alone might not achieve. The eventual fate of our sun as it evolves toward red giant status and eventually sheds its outer layers as a planetary nebula will return many of the stellar nucleosynthetic products currently organized into Earth's biosphere back to interstellar space, where they will become available for incorporation into future stellar and planetary systems that continue the cosmic cycle of stellar nucleosynthesis and element organization. Picture this distant future redistribution as a cosmic recycling event that will scatter the elements currently organized into Earth's geology, atmosphere, oceans, and life forms back into the galactic medium, where they will contribute to future episodes of star formation and planetary system development, ensuring that the chemical complexity achieved on Earth contributes to ongoing cosmic evolution. The deep time perspective that recognizes your stellar origins also acknowledges your cosmic future, with the atoms in your body destined to continue participating in cosmic evolution long after your individual existence ends, returning to environmental circulation where they will become available for organization into future biological systems, geological formations, and potentially conscious entities that continue exploring the creative potential of stellar nucleosynthesis. The meditation practices and philosophical traditions that recognize the interconnectedness of all existence find profound validation in the scientific understanding of stellar nucleosynthesis, which demonstrates that the separation between self and cosmos is largely illusory. You are not in the universe, you are the universe, locally organized into a form capable of self-reflection and cosmic understanding. Picture the dissolving of boundaries between self and cosmos that comes with understanding your stellar origins, recognizing that your consciousness represents a temporary organization of cosmic matter that enables the universe to experience itself while participating in ongoing cosmic creativity through awareness, understanding, and potentially technological applications of stellar nucleosynthetic products. The sense of cosmic belonging that emerges from understanding stellar nucleosynthesis provides profound comfort and meaning. Recognizing that you are not an accidental arrangement of matter in an indifferent universe, but rather an intimate expression of cosmic creativity that has been billions of years in the making through stellar evolution, chemical distribution, and planetary development. The responsibility that comes with cosmic consciousness includes recognizing that human actions can influence how stellar nucleosynthetic products continue to be organized on Earth and potentially beyond, with choices about environmental protection, technological development, and space exploration affecting the future evolution of consciousness and complexity in the cosmos. Consider how understanding your stellar heritage can transform your relationship with the natural world. Recognizing that every rock, tree, ocean, and living creature represents alternative organizations of the same stellar nucleosynthetic products that compose your body, creating a profound sense of kinship with all terrestrial matter and life. The humility that comes with cosmic perspective recognizes that human consciousness and civilization represent just one possible organization of stellar nucleosynthetic products among countless potential arrangements, encouraging appreciation for the vast creative potential that remains unexplored in cosmic evolution, while inspiring wonder at the remarkable achievement that consciousness itself represents. The gratitude that emerges from understanding stellar nucleosynthesis acknowledges the cosmic generosity that has made your existence possible through billions of years of stellar sacrifice, with countless stars living complete evolutionary cycles to create and distribute the elements that eventually became organized into your body, mind, and capacity for understanding your own cosmic origins. The sense of cosmic continuity that comes with stellar awareness recognizes that your participation in cosmic evolution continues through every breath, every thought, and every creative act, with your consciousness representing an ongoing exploration of the organizational potential of stellar nucleosynthetic products while contributing to the universe's growing capacity for self-understanding. The peace that comes with cosmic belonging recognizes that you're never truly alone, but are always connected to the vast community of stellar nucleosynthetic products organized into countless forms throughout the cosmos, with every atom in your body carrying the history of cosmic evolution, while participating in ongoing cosmic creativity through your existence and awareness. Tonight, as consciousness gently fades and sleep approaches, you can rest in the profound knowledge that you are made of ancient starlight, forged in nuclear furnaces that burned billions of years ago, scattered across cosmic distances through supernova winds, gathered into planetary systems through gravitational collapse, and organized through biological evolution into the remarkable phenomenon of self-aware cosmic matter capable of understanding and appreciating its own stellar origins. As you drift peacefully towards sleep, let the knowledge of your stellar heritage provide comfort and wonder, recognizing that your dreams tonight will be composed of the same stellar nucleosynthetic products that power the stars visible through your window, connecting you intimately to ongoing cosmic creativity while demonstrating that the universe's capacity for beauty, consciousness, and understanding flows through your very existence as an expression of cosmic love written in the language of stellar nucleosynthesis. Sweet dreams, fellow stardust, in the gentle embrace of the cosmos that made you possible.